Welcome back. Up until this point, we've talked about sorting algorithms that weren't very efficient and aren't that commonly used. Now, insertion sort is not the most efficient algorithm either, but there's cases where it's actually extremely fast, which we're going to talk about. So pay attention because this one starts to get important. You see, insertion sort is useful for times when you're pretty sure the list is almost sorted or it's already sorted, which sounds silly, but sometimes this is important in computer science. And in a best case scenario, you can get O of n, or linear time, when the list is almost sorted. Let's see how it works. We have a list and we look at 6. We look at the first item and just leave it where it is. We now look at the next item, 5. And because 5 is less than 6, we switch it over. And then we go next into the list. We say, hey, 3, where are you in relation to 5 and 6? Well, it's less than those two, so we shift those over and 3 gets placed in the front. So we now have this list of 3, 5, 6. We look at 1 and say, oh yeah, that's the first item. We want to shift everything, put 1 to the left. We then look at 8. Well, 8 is larger than all those items, so let's just attach it to the end of that list. 7, well, goes between 6 and 8, so place it in there. 2, between 1 and 3, place it in there. And 4, place it between 5, or 3 and 5. And that's it. This is probably the way that your brain works if you physically had Lego blocks with these numbers and you would move things around. And this type of sorting performs really, really well when it comes to small data sets, which we'll get into later on with our exercises. But can you do this type of sorting in code? See if you can implement your own insertion sort. Same thing as before. This time, we have the insertion sort algorithm. Based on the video and the YouTube dancers that I'll link to, can you implement your own insertion algorithm? In the next video, I'll show you the answer.